Let's try to visually illustrate that the sum of the first n odd whole numbers is equal to n squared, where n is a positive integer. Let's start with n equals 1. If we draw squares, we only get 1. Then let's add 3 by drawing 3 squares. Note that 3 is equal to 2 times 2 minus 1. The sum of 1 and 3 is equal to the number of squares in the figure. Note that from the row of 3, we move 1 square to the previous row to make a bigger square. Specifically, we are making a 2 by 2 square. Thus, the total number of squares here is 2 squared. By equivalence, the sum of 1 and 3 is equal to 2 squared. Let's continue this by drawing 5 more squares. Again, we can keep some squares at the third row and then move the rest to the previous 2. By doing this, we again make a bigger square. Such square is 3 by 3 this time. Therefore, the total number of squares here is 3 squared. Consequently, the sum of 1, 3, and 5 is also 3 squared. We extend this process to include more odd numbers. We see that for row n, which has 2 times n minus 1 squares, we keep n squares at the nth row and distribute the remaining n minus 1 squares to the previous rows. This applies to all. Note that for this pattern, the sum of the squares or the sum of the numbers up to 2n minus 1 is equal to the number of squares here, which in this case is n squared. As shown here, if you do this rearrangement, the figure beautifully rearranges into a bigger square every time. Note this can be extended inductively to any positive integer n. Just remember to keep n squares in row n and distribute the remaining n minus 1 squares to the previous rows. Isn't that amazing? Cool, really cool. Anyway, follow for more.